Welcome to Data Skeptic K-means clustering, the podcast exploring the problem, the algorithms, enhancements, and use cases for K-means clustering. Well, let's begin with a definition, which I think we can achieve in just 6 words. The objective you're trying to achieve is to partition n data points into k clusters. Let's check my math here, 6 words. Partition n data points into k clusters. Partition n data points into k clusters. Now let's take those 6 notes as our data and generate 2 clusters. Now I can do this in a lot of different ways. I could cluster them this way, or this way. But for some reason this feels the most natural to most ears. Our data is 2-dimensional. Each node is described by both its frequency and its position in the time dimension. Given data in 2-dimensional space, and the need to cluster the data into 2 groups, almost everyone's ears will intuitively prefer this version. And if you were to apply Lloyd's algorithm, the most popular approach to solving k-means clustering, providing it only your data and the number of clusters, k equal to 2. With no other direction, it would partition these 6 data points into the same 2 clusters. The how and the why of that is the subject of this season on Data Skeptic. It's one single algorithm, many variants, many use cases. Today's episode is a crash course on the topic. Whether you know it or not, I'm planting a bunch of seeds for things later to come in the season, overviewing the general research, and sharing a few of my own thoughts on this prolific algorithm. Our budget for this season has gone up considerably. We've just completed construction on our new demonstration room. Before me is a blank vertical canvas. It's 30 feet tall and about 55 feet wide. The painters finished the final coat of eggshell white this morning. And arriving now are our paintballers, who proceed to spray the wall in a pattern that looks a bit like the silhouette of Mickey Mouse's head. You've got the cranium and the 2 ears. But instead of producing 3 solid circles, our paintballers are spraying their paintballs at the center of their 3 respective targets. There's a bit of variance there. So in our 2-dimensional space, we have 3 2-dimensional Gaussian distributions. That is to say, more paintballs hit near the center of each gunman's target, but with some variance, they stray from the center point. If we imagine our data as being distributed like a bell curve, and that bell curve is in 2 dimensions, then as a whole, our data forms a 2-dimensional Gaussian blob. When it comes to k-means clustering, nothing is more perfect for analysis than Gaussian blobs of data. If your data set fits this format, you're in luck. Algorithms like k-means are built for data that's Gaussian blobs. But in the real world, data sets are rarely so well distributed. Okay, let's repaint that white wall again. Reset this whole scenario. Invite our paintballers to come back in, but this time, instead of being inspired by Mickey Mouse, they're going to be inspired by the classic smiley face image. Our first 2 paintballers come in and give us 2 nice Gaussian distributions for the eyeballs. And the 3rd paintballer comes in and completes this image with a nice swoosh across the bottom. That swoosh completes the mouth in our smiley face design. Now take a moment and picture this painting of a crude smiley face on the canvas of your imagination. Each of you has imagined a slightly different paintball smiley face. Mine has a lot of variance in it because I know paintball guns aren't really precision instruments. If you aim for one particular point, you'll create a cloud of points that we associate together because they share a common center or centroid, for which no member of the group is particularly far away when we measure the distance between their location and that centroid. If your data set includes noise or correlation of any kind, shapes like the smile and the smiley face can appear. While the human brain wants to intuitively set k equal to 3 for a smiley face and discover 2 centroids in the middle of the eyes, which is fine, but that third centroid, the centroid for the smile, it isn't even part of the smile. The centroid for the smile is somewhere on the upper lip. In fact, depending on how smiley your smiley face is, k-means is likely to slice right through the middle of your smile and counterintuitively place a few of those data points with a partitioning other than what your instinct says. With two-dimensional data sets, you can often catch these issues. A good scatter plot with colors to label the cluster assignments usually tells the full story. Your data can have any number of dimensions. Your dimensions could be geographic ideas, or they could be dummy variables or other kinds of features. Just as we saw some ambiguity in how the clusters might exist for a smiley face, you should apply a good amount of skepticism to what your clustering results really mean. Algorithms like k-means always give you a result. If your dataset is generated by some intuitively clustered Gaussian blobs, you'll likely recover that result. If your data is generated through a series of random coin tosses or lottery numbers, you'll still get a result. It'll be up to you to determine if that clustering result is informative or not. And there are many other factors to be cautious about that we'll revisit later in the series. But for now, don't panic. Let's explore the algorithm before we cast our skeptical eye on its results. When just about anyone talks about k-means clustering, they mean Lloyd's algorithm. There's alternatives and improvements to this classic algorithm, some of which we'll discuss in upcoming episodes. But for now, let's step through the plain vanilla Lloyd's algorithm. It comes in 3 steps: initialization, assignment, recalculate. The initialize phase is actually rather trivial. For whatever k we're going to use, let's say k equal to 3, you randomly select 3 points and place your initial centroids at these random locations. It's very much like throwing 3 darts at the wall. Surely there's more intelligent ways to initialize the problem, right? A popular approach is called k-means ++, which we'll cover in the near future. But for now, throw 3 darts at that paintball painting on our 2-dimensional canvas. Once that's done, consider yourself initialized. Those 3 darts represent our initial centroids. Let's move on to steps 2 and 3. Assign and recalculate. During the assignment step, you scan through every data point. Compare each data point to each of your centroids. And regardless of what cluster you thought each data point might have been in the past, assign that individual data point to the nearest centroid. Once you've assigned every point to a centroid, step 2 is complete. We move on to step 3, recalculation, in which we formulate the new version of the centroids. In the assignment phase, we may have reassigned a bunch of different data points. The centroids we previously calculated might have moved a little bit. So we average over all the points in each of the assignments and calculate some new centroids that may have moved from their previous location. Having done that, we can now go back to step 2 and repeat the reassignment. If any points shifted, those will have moved the centroids a little bit, and hopefully the amount of change is declining over time. It's actually possible to get caught in an infinite loop here, so you will definitely need to establish some sort of halting criteria. Okay, let's get a little bit more technical now. K-means clustering is the poster child for unsupervised learning. We use the word unsupervised to contrast with supervised learning, in which you have training data that is labeled, and the objective is to learn a function that can predict the true label on unlabeled future data. But like many things in life, that sounds a lot more binary than it actually is. You can bucket algorithms like logistic regression and random forest into the same bin of supervised learning, because essentially they're trying to solve the same problem, just with different methods. Unsupervised learning, on the other hand, is more of a grab bag for unrelated machine learning tasks linked together only by their common property that they don't require labeled data. In terms of commonality, unsupervised learning is like my club that you can only join if your first name starts with K. So Lloyd's algorithm requires one parameter, the famous k in k-means. If your dataset has n elements, Then there are k to the n possible labelings you could output. As your dataset grows, the number of options grows exponentially. Yikes! There's no way we can check every possible combination of labelings to find the best one if that n gets too big. This is a classic search optimization problem. Optimization problems involve finding the best answer you can out of all possible answers. In our case, best needs to be numerically defined. The winning example wins our favor because it minimizes the distance from each point to its associated centroid. Our distance metric is a function that effectively scores each solution, and we need an algorithm that's going to find its way to the best score. For this optimization problem, the best score is the one that minimizes the average distance between your data and the associated centroids. Remember that we've got k to the n possible labelings, so as the size of your data gets larger, it gets exponentially harder to do an exhaustive search. Instead, we treat it like an optimization problem, searching for the optimal solution. However, that search comes with no real guarantees. Our search may get trapped in some local optima if we start with an unlucky initialization. Solving the general case of this problem is NP-hard. If you don't know what that means, don't worry. We've got a few good computational theory episodes in the archives that will help you, but it's not important for this season. The key takeaway is that a clustering result is not guaranteed to be the best possible result. Go ahead and use whatever library you can find for k-means clustering. You will get a result. It's not certainly the best result, but it's probably a good one. In practice, this is an important subtlety, but one you don't have to worry too much about. In practice, I worry much more about the underlying shape of my data and how suitable it is for k-means, more than I worry about how epsilon close I'm going to get to perfection. Remember, k-means works best on these Gaussian blobs. If your data is in that format or can be transformed into that format, it'll work great. Thanks to our sponsor, Hellofresh. With Hellofresh, you get farm-fresh, pre-portioned ingredients and seasonal recipes delivered right to your doorstep. Skip trips to the grocery store and count on Hellofresh to make home cooking easy, fun, and affordable. That's why it's America's #1 meal kit. Linda and I are both busy working professionals, so skipping the trip and getting just the right portion of ingredients for some really creative recipes is a huge bonus for us. HelloFresh cuts on the time spent in the kitchen. Most of these meals are like 30 minutes prep. There's really low cleanup, and it's even something we've been slipping in as a nice lunch break. HelloFresh offers 50 menu and market items to choose from every week, which is important because Linda's a vegetarian. They always have a great veggie option, fit and wholesome, family-friendly, and gourmet options. There's plenty of variety. In fact, I'm waiting for Linda to go out of town so I can switch our account over for that week, maybe get me the beef tenderloin and cheese fondue, or better yet, the miso, sesame, shrimp, and bacon ramen. Go to HelloFresh.com/DataSkeptic16 and use code DataSkeptic16 for up to 16 free meals and 3 free gifts. You can't beat a deal like that. Check out America's #1 meal kit at HelloFresh.com/DataSkeptic16. Thanks to our sponsor, Mparticle. At the end of the day, your customer has to be at the center of everything you do. This starts with the right customer data strategy, as well as the right foundation to solve the challenges that typically inhibit success, such as data quality, data governance, and connectivity. Mparticle is your real-time customer data infrastructure that helps you accelerate your data strategy by cleansing, visualizing, and integrating your customers' data from anywhere to anywhere. Ultimately, better data leads to better decisions, better customer experiences, and better outcomes. See why the best brands choose Mparticle. Visit mparticle.com to learn how teams at Postmates, NBC Universal, Spotify, and Airbnb all use Mparticle's customer data infrastructure to accelerate their customer data strategies. That's Mparticle. Better data, better decisions, better outcomes. Visit mparticle.com to learn more. Now let's talk about one interesting pitfall. Imagine you have some data on different automobiles. You have the year of manufacture, the average miles per gallon, the manufacturer's suggested retail price, and a few other statistics about various cars. For whatever reason, you've decided to cluster your car data, and you've decided to blindly apply k-means clustering, Lloyd's algorithm. Let's review our variables. We have the year of manufacture. This data set might go back to, the 1970s maybe, up to the present. In other words, ranging in integer values from 1,970 to 2,022. Second variable, you have miles per gallon. That's an interesting one because currently there are gas cars, hybrids, and electric cars. I've had a hybrid for the last 8 years that gets 40 to 45 miles per gallon. Back when I had gas-only cars, I remember getting about 20 miles per gallon. And I don't even know what our spreadsheet should say for all electric cars. 0 miles per gallon, infinite, -1. Let's just ignore that for now. I also mentioned retail price. Some cars sell used for a few $100s. Less often, cars can sell for hundreds of thousands of dollars. Think about these ranges. The year of manufacture covers a roughly 50-year range. Miles per gallon, it's a little smaller variance. And the retail price, that presumably has a pretty large variance if we measure it in US dollars. Units matter. If you blindly ask a machine learning algorithm to solve an optimization problem on data like this, it will absolutely exploit the unnormalized nature of your data. If the x-axis is in years, and the y-axis is in miles per gallon, and the z-axis is in dollars, then the biggest distance between your data points are actually going to come on the z-axis, where price has the largest range of the three variables. A very naive implementation of k-means clustering would yield an automobile dataset clustering result that is based primarily on the price while ignoring the other variables. Hey, it's unsupervised learning. Who's to say what's right? But clearly something is wrong if we do this blindly. And that's why most software implementations of k-means clustering will automatically apply normalization of your data in a standard statistical way so that units can't bias your results so significantly. In practice, you don't need to worry about this. These concerns are probably going to be handled under the hood by the software you use. However, if your clustering result is going to inform an important decision, maybe a decision that has millions of dollars on the line, it might be worth a deep dive into making sure that your dataset fits the problem very well. Another variable you'll need to consider is the size of your data. The vast majority of listeners will never encounter the scale of data set that requires you to take special care. For most of you, your interaction with k-means clustering is likely to fit snugly into memory, such that you can use practical tools like sklearn to do a one-time process to cluster your data. Even if that process has to run overnight on a couple of computers, so what? You get your results Monday morning when you get back to your desk. On small data sets processed with modern compute, your clustering results are going to be available pretty quickly. I really can't imagine an urgent decision that might need to be informed by the results of our clustering effort. So in practice, and informed only by my limited anecdotal experience, I found no intrinsic virtue in arbitrarily clustering some data. In each of my use cases, k-means has only been one step in a bigger recipe, typically as a feature engineering step. Given some input data, you can apply Lloyd's algorithm or some variant to develop an efficient classifier that can label my underlying dataset in some meaningful way. Every time I've personally used k-means beyond a classroom level analysis, it's been in pursuit of pulling a new label out of thin air, essentially, like a magician. Should I trust that label? No. Always be appropriately skeptical of your input data. But if your data does exhibit some modal property and k-means is able to recognize that, then the clustering of each of your data points gives you an opportunity to assign a new label. And you get that seemingly for free from this unsupervised algorithm. And maybe if you take that label and you pass it on to some other process, typically some supervised learning process, which can in turn use that cluster ID as a feature, and if that's a useful feature, then the data speaks for itself. Now to wind up, let's talk about two remaining topics I want to cover that relate to k-means: the elbow method and silhouette scores. Now, as I mentioned, the way in which k-means has been personally most useful to me is to take an existing data set and squeeze an additional feature out of it. For any particular observation or transaction, what cluster does that element belong in? And if that's a useful feature to me, it's based on k-means clustering, so it really begs the question, what's the best k that I should be using to suit my needs? And there's for sure no provably best solution here. It's really all about trade-offs. If you select a large K and therefore use more clusters, those clusters obviously fit the data better, but at some point they undoubtedly begin to overfit the data. To make a decision like how many clusters should I have, most people will recommend the elbow method, in which you create a plot of K on the x-axis and some metric along the y-axis, and typically that metric is the explained variance. The explained variance measures how well the cluster fits the data. So if we think at the far end, let k equal to n, then every data point lives in its own cluster. It's a perfect overfit example. There's no variance in the group, and thus 100% of the variance is explained because every data point snugly fits into its individual cluster. Now picture the curve we would get if we look at the scores from k equal 1, where there's a single cluster, up to k equal n, where every data point is in its own personalized cluster. That curve will certainly be increasing. And the hope is that if you visualize it, it'll demonstrate some sort of elbow in that curve. That is a sort of obvious point of inflection for your data, suggesting where your k should be selected. In practice, my personal experience is that this is a very subjective process. Your mileage will definitely vary. And that second method I mentioned is silhouette scores. While I'm not super hot with the elbow method, I do really like silhouette scores. It's a deterministic single value that's painless to compute and gives you a nice quantitative signal. It's based on two variables. First, the average distance of all points in a cluster from their associated centroid. Naturally, we want that to be small. Second, it's the average distance between each point and the other centroids that we presume it's not a part of. We assume that mathematical value will be very large, and as a result, we have a nice arithmetic way that we can score ourselves between -1 and 1, and that score hints at the quality to which the clusters we've calculated fit our data. So in this season of Data Skeptic, we're going to be celebrating the poster child of unsupervised learning methods, k-means clustering. If you have a data problem, and if no one else can help you, and if you can find the centroids, maybe you can apply k-means clustering.